All right, so we now, in this part, are going to discuss the issue of determinacy and indeterminacy. Very important. Determinacy and indeterminacy. Okay? Now, a quantity is said to be statically determinate if its value is determined exclusively by the equations of statics. So that's it, right? If you can calculate whatever you're asked using only statics, that means that statics is all that matters as far as that quantity is concerned, and therefore that quantity is statically determinate. If it turns out that statics is insufficient for you to be able to determine the value of the quantity that you were asked, then that quantity is statically indeterminate. Means that it's not that statics is not applicable. Of course it remains applicable and it has to hold, but it is not enough. That means that properties of the material that the structure is made and so on also play a role on what the value of the quantity is. Now let's illustrate, because it's an intuitively clear concept, right? If I have a beam and that beam had a load P in the middle, I'm making it as trivial, as simple as possible so that we don't get all, bent down on calculations. If I say what is the reaction at A in the vertical direction and what is the reaction at B, everybody knows it's P over 2, and all you needed to do was use statics. Therefore we say that these quantities were statically determined, right? Now, if I take the beam and I put one more reaction, let's say one additional support here, now the beam has 3 supports. And now I put, let's say, a uniform load on it, which is W kips per foot. And let's say that these distances are both A and A. Actually, you know what? No, I changed my mind. Let me now bring symbols in at this point. Let me just do this. I take the beam, I put 3 supports, a roller here, a roller here, and a pin here, and I put 2 loads, both in the middles of each beam, both equal to P. Now, if I ask what is the reaction at A, the reaction at B, and the reaction at C, it turns out that you cannot calculate the reaction at A, the reaction at B, and the reaction at C exclusively from statics. Why? Because statics in a 2-dimensional problem like this, in this case, gives you only 3 independent equations, some of the forces in X, some of the forces in Y, and some of the moments, or an equivalent set, and you have 4 unknowns, 1, 2, 3, and 4, right? Now, you might say, wait a minute, I know this one is 0, I only have 3 unknowns. Yes, you know this one is 0, but you already used one equation, which is sum of the forces in X equal to 0. So now you have 3 unknowns, but you only have 2 equations left. The point is, you cannot calculate those 3 reactions using statics only. Okay? Now, let's see. So we would say that this reaction RA, or this reaction RB, or this reaction RC is statically indeterminate. However, if I ask you for the sum of RA plus RB plus RC, then you can certainly say that that is 2p, right? Therefore, the quantity defined by the sum of the three reactions is statically determinate, even though each of the reactions is indeterminate or cannot be computed from statics. Okay? Consider, let's say, something else. Let's say you have now this being fixed on this side, goes like that. Let's say we have a roller here, and let's say another roller here, and then it keeps going. So this is A and B and C and D. Now I can put some loading on this beam. I don't know, maybe I'll just, let's say we call these distances L1, L2, and L3. And let's say that I have a load here, and a load here, and a load here. Let's say they're all P in the middle, and this one is at the end. So, if I say, how many reactions are there? You would say, well, 1, 2, 3, 4, and 5. So I have 4 reactions. And how many equations of statics do you have? You have 3. Therefore, you cannot solve for these reactions using statics only, and you have to conclude that that structure, that quantity, each one of the reactions, is not computable from statics, and therefore is not a determinate quantity, it's an indeterminate quantity. However, if the question was what is the moment at C, then you can take this free body diagram, and from that free body diagram you can see that this is the moment at C, and there is a shear and there's an axial, and so you can see that the moment at C, so many moments about O minus MC plus P times L3 is equal to 0. So the moment at C is PL cubed, PL3, right? Therefore the moment at C is a statically determinate quantity, even though there are indeterminate quantities in the structure, right? Doesn't even have to be a sum of anything. I can calculate the moment here, I can calculate the shear here, it's just P and so on. I can't calculate it over there because I cannot come up with any free body diagram, any bubble that will allow me to find the values there from statics. Let's see. For example, if you say, wait a minute, I'm going to get clever. You say, I can't do it, but maybe I can, right? No, you can't. So you say, well, what is it that you want, the moment here? Okay, so I'll take, let's say if I take a look at that bubble, right? So if you take a look at that bubble, you find that there is a reaction here that you don't know, right? And then there is the load P here. And then there is the load P here, let's say. Those are not a problem. And then you cut here, right? So here there is a shear, there is an axial, and there is a moment. Now, how many unknowns are there? 1, 2, 3, 4. How many equations of equilibrium do you have in that? You have 3. Therefore, you can't solve for 4 things using 3 equations. Now, again, you could say, but I know this one is 0 from some of the forces in X. True, but you already used one set of equations. Now you have 1, 2, 3 unknowns and only 2 equations. So you can't find that moment. Okay? In the case where a quantity is statically indeterminate, it means that its value depends on things, depends on relative stiffnesses in the structure. So let me see if I can give you a very clear example. Consider this beam. and then consider let's see, will that be clear for you or not? Yeah, let's say we have this, another reaction here, and let's say that in the middle of this I put a P load, right? And let's say this is A and B and C. So let's say we ask the question, what is the reaction at A? Well, I can see that there's 1, 2, 3, and 4 unknowns, and I only have 3 equations, so I think that the reaction at A is going to be statically indeterminate. That means that statics is just not going to be enough to calculate. I'm going to have to learn something new. But now, why is it that it's not enough? For the following reason. If you can visualize deflected shapes in your mind, perhaps you can see that this beam is trying to lift off point A, right? In other words, that this beam is kind of deforming like this. So this point wants to lift this up, right? So we do expect that this reaction is down in order to hold point A in place. So far so good, right? Now why is it that I can't do it with statics? Well, for the following reason. Imagine that the beam from here to here is made of balsa wood. Or what do I want to say? From here to here, no, I don't even have to change that. Let me just make it with a sketch with size. Let's say that the beam from there to there is like this, and then it gets really very thick in relation. And so it's like this now. And then we put the load here, and then we have the reaction here. Okay? So, if I make this side very stiff compared to that side, what do you think happens? If you can't see it, just keep pushing the issue. Keep making this thing thinner and thinner, right? At some point, it doesn't matter what you have there, right? So in the limit, you're going to have P over 2 and P over 2, right? Because this thing hardly bends enough to produce any effect on this side that this matters. So this will go to P over 2, that will go to P over 2, and that will go to 0 as we keep making that smaller. But from a statics point of view, you don't see anything, right? Now, the fact that I make this thick and this thin, I could have left them all the same size, and I could have just simply say that this here was made of steel, and this here was made of soft wood, which is hundreds of times more flexible, starting at this point, and we would have gotten the same conclusion. It would be the same as this. This part is so stiff that when you put the load here, almost everything goes half and half to these two supports. All right? Therefore, statics does not suffice to tell you what the reaction at A is. You would have to know what's going on with stiffnesses on the structure. And the ability to solve for quantities that are not statically determinate is what remains out of this class. That is, you need to expand your toolbox from statics to quantities that are not statically determinate. In fact, in reality, most structures are such that most quantities are not statically determinate. Therefore, statics is an essential tool, and it's obvious, not only an essential tool, is an absolute constraint that must be satisfied, but it does not suffice, it is not sufficient to solve the structural analysis problems that we face typically every day. So, now, in civil engineering, we are not particularly have not been traditionally that concerned with being really precise, I guess. And so in the common language of civil engineering and in books, you do not find this emphasis that I have made here to separate the issue of statically determinate and indeterminate as applying to quantities. And the books and the normal discussion usually refer to statically and indeterminate structures, as if it were the complete structure that was statically determinate or indeterminate. That is actually a sloppy way to describe it, but it is the way it's done. So after I assume that you understand what I'm talking about here, that the question really applies to quantities, we will be using the terminology, because it's commonly used, statically determinate structure and statically indeterminate structure. Basically meaning that if there are statically indeterminate quantities in the structure gets lumped as being statically indeterminate as a whole, right? Now, for those with a mind like the way I like to approach these problems, the static determinacy problem of applying it to structure is even a little bit more problematic than what I just said, because even if you look at the simple case of a simple beam, right, like this, you would say, wow, that's the most statically determinate situation in the world, right? I can calculate these two reactions right away by looking at it. They are P over 2. I only needed statics. I can do my shear diagram from statics. I can plot my moment diagram from statics. And once I have my shear and my moments, I can calculate my stresses from My over I, right? I can calculate my shear flows as VQ over I, from where I can calculate my shear stresses as the shear flow over thicknesses. I can do everything, right? And it's just from statics. Well, not really. You can do everything that we normally do most of the time, but that doesn't mean that you cannot come up with, for example, if I tell you that what I have in this structure is in this beam, is a temperature change that is like this. That is, I have a nonlinear temperature across the beam. Then if you wanted to know what are the stresses due to these temperatures, which we don't do because it's not a subject that is part of elementary structural analysis, or structural analysis to the level that we handle it in undergraduate. But if you had a nonlinear temperature distribution, there would be stresses in here. And you know what? Those stresses would be statically indeterminate, in the sense that you cannot calculate them from statics. They would depend on what the material is and what are the fibers made of, and they would differ if half of the beam was wood and half of the beam was steel. Okay? The shear diagram would not change, the moment diagram would not change, the reactions would not change, but the stresses due to a nonlinear temperature distribution would change. If it was just one material, or if it were two materials like that. So, if you really want to be clean mentally, you have to just say that all there is are just statically determinate quantities, not statically determinate structures. That the use of the term statically determinate structure is just a conventional thing. That what we mean is, if we can calculate shear and moment diagrams using only statics everywhere, that's good enough. We're going to call it statically determinate structure. Okay? Now, a structure may be statically determinate, may be statically indeterminate. Let's take a look at trusses. If you have this truss, which is like, let's say, your classical truss, right? It has a name, but I forget. We know how to do that. You've been doing something like that for a while now, and you're an expert in doing those calculations. So that is obviously all you needed to know was statics, right? So we would recognize that structure, that truss, as being statically determinate. Now, how can we have a systematic computational approach for trusses to see if it's statically determinate or indeterminate a little bit quicker, right? Or more systematically. So one thing is to say, how many joints does a truss have? That's easy to count. So we can say J is the number of joints. Now, how many equations could you write at every joint? Well, if you look at a free body diagram of each joint, you could write two equations, right? Because some of the moments would make no sense. It's a point. So if you took free body diagrams around each joint, you would have 2 times the number of joints for equations. So the number of equations equals 2 times the number of joints. Now, how many unknowns are there? Well, let's say B is the number of bars. And let's say R is the number of reactions. So the unknowns in the problems are the number of bars and the number of reactions. So the number of unknowns is the bars plus the reactions. So we would say that a truss is statically determinate, or at least appears to be statically determinate because there's one more option, if 2J is equal to B plus R. Okay, that means statically determinate. Now let's count them here. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 joints. Bars, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, I don't know if I missed the vertical. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so we have 13 bars. And how many reactions? 1, 2, 3. So we see that the total number of unknowns is 16 and that 2 times the number of joints is 16, and yes, this structure is statically determinate, right? So that's a way to count for trusses. If in this problem we went like this and added another bar there crossing, then the number of bars would not have been 13, would have been 14, right? And so the total number of bars would have been 17. And then we would have said that the structure is not determinate, it's indeterminate. And this brings us to the idea of how indeterminate. So the degree of indeterminacy in this case would be 1, because we have one too many things. Okay, I will make further note on that. So that structure would then appear to be indeterminate to the first degree. However, when you do a count in a truss, you may conclude that it's determinate, or you may conclude that it's indeterminate to the something. But it is always possible, no matter what the count, that the bar arrangement is bad, and that this, well, if 2J is less, if 2J is more than B plus R, right, then that means that you have too many equations, and in that case there's only one conclusion, which is that the arrangement is unstable. Okay? What am I doing? So if you have 2J is more than B plus R, the arrangement is unstable. So in this case, if I had taken these 2 bars out, right, then instead of having 17, we would have had how many? We used to have 13, now we would have 12, and so now the sum of the unknowns is 15, and we have 16, and so we would conclude that the truss in that case is unstable. Now, it's unstable, right, because it needs something to make this part here rigid, and it doesn't have anything in this square, and so that is an unstable arrangement. I think we can see right away that that just would not really hold the loads if we apply loads to it, right? So that's an unstable configuration. Why do I say you have to be careful? Because you may have a situation that that one is unstable, right? It's unstable because it's missing one bar. But now if you do this and you do the count would seem to say that it's determinate, right? But it's still unstable because that bar was not needed there, it was needed here, right? Therefore, instability when you draw in a structure is an issue that, well, if a certain count doesn't satisfy some limits, like in the case of the truss, if 2J is more than B plus R, you can sign with 100% certainty that the truss is unstable because you have too many equations for the number of unknowns. However, if your count tells you that the structure is either determinate or that it's indeterminate to the degree 1 or 2 or 3 or whatever, there is always the possibility that the structure is actually unstable, okay? And the instability is from the arrangement. There is no simple approach to check for instability that can be done for any structure without in-depth knowledge, or modern methods allow you to do that without too much problem, but they are beyond the scope of the class. We can investigate the stability by investigating eigenvalues of the stiffness matrix and so on, but those are a little bit more advanced topics. At our level, really what is important to recognize at this stage, so you get yourself into this topic, is this, because all this stuff is rather evident if you have a reasonable engineering intuition, right? And you've been able to develop it in your studies as you go. So if we have that, that looks good, right? So that is a determinant, and if you do the count, that's what's going to happen. You're going to find that the structure is determinate and all is good. If you go like this, the count's going to show indeterminate to the first degree. If you go like this, now it's indeterminate to the second degree. If you go like this, now it's indeterminate to the third degree. If you go like this, now it's indeterminate to the fourth degree. Now if you go like this, it may look like it's indeterminate to the third degree, but it's actually unstable, right? Because that panel does not have the ability to transfer shear across. Also, to emphasize my point from before, even though 1, 2, 3, 4, even though that is indeterminate to the fourth degree, if we put that loading on it, we cannot calculate the bar forces from purely statics because there's not enough equations. However, 10, 20, 30, 40, 50, 60 symmetrically placed, those reactions are 30 kips, right? Therefore, those reactions are statically determinate, even though the structure itself is indeterminate to the fourth degree, right? Okay, now a little bit about determinacy and indeterminacy in frames. Let's see. Let's begin with this one. That frame is determinate. Why? Because there's 1, 2, and 3 reactions, and once I have those reactions, I can take a bubble that only cuts once. So I can calculate shears, moments, etc., having only the unknowns where I'm cutting, right? You want to know what's going on there, you go like this, and that's it, right? Once you have these reactions, you have 3 unknowns. So that structure is determinate. Now, less obvious, well, okay, no. Now that structure is not determinate. Why? There's 1, 2, 3, 4, 5, 6 reactions, right? So there's 6 reactions. You only have 3 equations of statics. So you have to say that that structure is indeterminate to the 3rd degree, right? 6 versus 3. Now, if you knew the reactions, you could calculate what's going on, because then you could take the bubble, but you can't get the reactions. So that structure is indeterminate to the 3rd degree. However, how indeterminate is this one? Well, that might be a little bit less obvious, right? Because you cannot just count reactions, right? I mean, you can count reactions, and there's 3, 6, and 9, right? So from the fact that there are 9 reactions and you have 3 equations, you might think, okay, it's indeterminate to the 6. No, it's more, right? Because even if you have the reactions, okay, let's say you've got the reactions, and let's say you want to get the moments and shears and so on at where I just put this mark. If you wanted to do a bubble to get that, you could go like here and say, okay, I know the reactions, I cut through here, but how do I come out? Well, it looks like the quickest way out is this way, right? But now I have 3 and 6 unknowns. Therefore, even after I have these reactions, I still can't calculate what's going on at this cut from statics, because I have to cut 2 times. So in frames, the situation is more, well, less apparent perhaps at first glance. But it's really easy to actually find out how indeterminate it is by recognizing the following. If you look at a tree, T-R-E-E, if you look at a tree, trees are always statically determinate. This is a tree. Right? A tree is always statically determinate. Why? Because the tree is connected to the ground and there's 3 reactions, right? Fixed ends. And then if you want to know what's going on anywhere, take your pick. So you want to know the shear moment and axial force over here. Okay, so you can always take a bubble that only cuts there, right? And therefore only 3 unknowns will show up. So trees are statically determinate always, no matter how complicated the tree is. Therefore, what we do when we have a frame is that we open it up into several trees. So what we want to do is imagine that this is, so you open it here, you open it here, you open it here, you open it, because trees don't close, right? And now you can say that you have 1 tree here, right? 1 tree here, and 1 tree here, right? So now that you opened it into a tree, or 3 of them, then you can see how many unknowns did you create by this cut. 1, 2, 3, the same 3 on the other side. In this case, 1, 2, 3, and the same 3 on the other side. So every time you open, you had to get rid of 3 things, right? 3, 3, 3, 3. So how indeterminate is this frame? 3, 6, 9 times 2 is 18. So this frame is indeterminate to the 18th degree. All right? Now, it doesn't have to be like that, right? It could be like this. Even like this. Even like this. How indeterminate is that structure? Well, I have to open it into a tree, so that's it. Right now it's this tree, and this tree. So I got 3 here, 3 here, 3 here, and 3 here. Therefore, that structure is indeterminate to the 12th, right? Okay. Now, there are some instances where the frame, let's say this frame, so let's start with the frame like this. How indeterminate is it? I'm not going to open it. It's just obviously 3, 6, 9 times 2 is 18, right? So we start with that frame would be I18. But now let's say that this support was not fixed, but was a pin. Then what happened? I got rid of one moment here, so now the structure became I17, right? Now what happens if in addition to that I put a hinge here? That means that I know that the moment at that place is 0, and therefore this structure is now I16. And if I do this, 15, 14, 13, 12, 11. So that structure is indeterminate to the 11th. Again, I would cut open 3, 6, 9, 18, 17, 16, 15, 14, 13, well, wait a minute. 3, 6, 9, 18. Now I start under here. 18, 17, 16, 15, 14, 13, 12, 11. So that structure is indeterminate to the 11th, right? Now, does this work no matter how foolish you want to be with putting hinges and so on? No. Because, for example, if, let's take all the hinges away and let's put this back. So let's say we're back to, this is an I18, right? Now let's say that you put 3 hinges here in a row on that beam. You might say, okay, this is now I15. No, that is unstable, because now you have the ability for this part to move down without any restraint, okay? And so the possibility of unstable arrangement is always there, and one should always keep your mind open. We do not in this class attempt to force the issue with regards to you being able to tell unstable structures that are not immediately obvious or something like that, right? But you should be able to determine the clear cases of instability, but primarily how indeterminate a structure is, that you have to be able to do, right? Now, let me see, I don't think I had much more on that. Yeah, let me just say that, for example, consider that structure. It's a frame. Is it determinate? Is it indeterminate? Is it unstable? Okay, the answer is it's not unstable, it's stable, because it's just, well here, and that's rigid, connected, everything. Can I get the reactions here? Yes, because there's 3 reactions, so a free body diagram of the complete structure will always allow me to get the reactions. But is it determinate? Actually, it is not, because what? Let's say, I'm going to show you, the tree calculation shows you it's not. But let's say we want to do it with the basic test that says, okay, I can calculate these reactions, right? I can. But now I want to know what is the moment here. So what do? I need a free body diagram, right? That cuts through there. And so I go like this with this bubble, and I cut through it. But how do I get out? Do I get out through there? That's going to cut again. Do I get out through here? That's going to cut again. So I cut again, and I see 3 unknowns here, 3 unknowns here, so I'm going to end up with 6, and I can't solve. And it doesn't matter what I do, I just can't solve. Therefore, that structure is not determinate, is indeterminate, and is indeterminate to the third degree. And the idea of the tree makes it clear, because it's one tree, right? But trees don't do that, they're open. So you can open it up. Now that's a tree. Here's a branch, it stopped there. Here's the other branch, stopped there, right? And then when you did this, how many unknowns were there? 3. Axial shear and moment. Therefore, that structure is I3. Okay? So that is determinacy and indeterminacy basics. All right? Okay, let me stop here this module. I'll check to see how much time has been used.